Our next speaker is Mark from Bosch, who's going to talk to us about multi-component flow in SU2. And looks like you're here. Thanks for turning on the video, Mark. Take it away when you're ready.
Okay, thank you for the introduction, Thomas. So welcome everybody. I'm Mark Heimgartner. I'm a master's student mechanical engineering at the University of Twente, located in the Netherlands. And the past few months I've been busy with implementing composition-dependent fluid properties in SU2 under supervision of Nijso Bijshuizen and Edwin van der Weijden. So a bit about the applications. On the right here we see a burner, and what happens is that when the fan is turned on, air is sucked into the venturi, and here is the venturi located, and it creates an underpressure. And by this underpressure, the gas is sucked in. So basically, this venturi, which I'm currently circulating, is basically a device which mixes air with fuel in the right mixture properties. I need basically two things: an equation for transported scalar, which is already implemented in the feature flamelet, and I need mixture-dependent properties. Next slide, please. Yeah, so a bit about the research objective. Oh.
There may be just a tiny bit of lag, but you should be able to click back and forth. If not, just say next and Juan can click for you.
Okay, I will turn back. Yeah, this slide's correct. So on the right, we see a cross-section of the venturi. So here we see the intake of gas via a gas nozzle, and here we have the air intakes, and then here the mixing happens. So I have a transported scalar, which means that the presence of the scalar influences the flow field. So there's a coupling which we need to capture. And the final goal of the assignment is to perform a multi-point design optimization using a joint solver. Because right now what we currently see here, we have a characteristic curve of a boiler, and it measures the CO2 emission at the outlet of the venturi. And the problem is that at lower heat outputs, the gas flow should be increased, and for that we want to change the geometry of the venturi by means of an optimization process using the joint solver. But first we have to implement mixing properties such that we have the correct capturing of the flow. So here we have the mixture laws. The most important thing is that for the viscosity I use Wilke law, and it basically is not a linear relationship, as you can see. And what also works is that you can still use the species fluid properties which are currently implemented. So for example, for the viscosity, you can still use the constant viscosity or a subtlant or a polynomial viscosity model. The binary diffusion coefficient is based on a Lewis unity assumption, which means that no new parameter is introduced. I just use the conductivity, the density, and the specific heat to compute the mixture diffusivity. Here we see a performance of the mixture viscosity models. So I plotted Wilke law, and Davidson is just kind of a similar law, but I will not go into depth right here. And it does work quite well. There are some underlying assumptions in using these models, which do not typically hold for my mixture, but we see that it's still quite reasonable accuracy. So a bit about how I implemented this in SU2. I introduced a new fluid model called mixture fluid model. And this mixture fluid model can be accessed via a new class, C fluid scalar, which inherits from C fluid model. And in C fluid scalar, I have a function called setTD state t. And at every iteration, the density, the viscosity, the conductivity are calculated for every point in the domain. And this is only implemented for the incompressible solver. And what's also important to notice is that the existing architecture for the fluid properties can still be used. So the user can still specify whether he wants a constant viscosity or a turbulent model, for example. How to access this in SU2? So you have to specify the fluid model, mixture fluid model. And then for every property you have to specify an array of the amount of species you have. For example, if you have a mixture of 2 species, you have to specify the molecular weight of each of the species and the viscosity of each of the species. And as well, you also have to specify the diffusivity model, which is unity-Lewis, as I mentioned previously. In the future, I can also add non-unity-Lewis when you have, for example, mixing with hydrogen, which has a Lewis number of about 0.3. So a bit about the setup. It's what I've currently done is a planar situation, so it's 2D. I tried axisymmetric in SU2, but it did not converge. So I will look after that and figure out how to fix that issue. I used the SST turbulence model, and there's no heat transfer and also no reacting. It's just mixing. I use a velocity inlet for the gas and the air intakes and the zero pressure outlet. And well, I have a symmetry boundary condition here. And for the results, I've extracted well, the fluid properties at 3 locations in the venturi. So the residuals, it converges quite reasonably. It drops about 4 orders of magnitude. It can still be a bit better though. Now I refined the mesh near the mixing of the air and gas street. And fluid meshing has been used to make this mesh. So here we see some actual results of a comparison between SU2, what I've been implementing, and Fluent. And here we see the locations at 3 different points in the venturi. So 0.3, 0.217, and 0.304 meters, which is at the outlet. And with these, we do see quite reasonable agreement between SU2 and Fluent. The mixing can be a bit better. We see that as we go downstream the venturi, it gets better, but well, ideally we would have a homogeneous distribution of the mass fraction of methane. So similarly for the mixture viscosity and mixture conductivity, which do also agree reasonably. And for the mixture density and the binary diffusion coefficient, also quite good agreement. So here we see some contour plots. On the top side, we see the results of SU2, and on the bottom of Fluent. Everything it's quite nice. It's the accuracy is quite good. But to get some further well info, we should zoom in a bit. So here we see again the density, the laminar viscosity, and the turbulent kinetic energy. It's very similar contour plots. So finally, here we see a more detailed comparison. I plotted the contour lines of the mixture fraction of the mass fraction of methane from 0.8 to 0.55. And also I computed the pressure drop across the venturi and the mass flow average mass fraction of methane at the outlet, which also agrees reasonably well. The goal is to finally have a homogeneous mass fraction distribution. So we have to optimize the venturi geometry using the adjoint method in order to have a homogeneous distribution. So it's still work in progress. There are still some minor discrepancies downstream after the air and gas rejoin. That's not something to worry about. The accuracy is quite good in agreement, but performance does vary a bit. Fluent was done in 5 minutes and SU2 took about 53 minutes. So it's about factor 10 faster in Fluent. And well, overall, the mixture laws have been correctly implemented and it works all well. The next step is to merge this feature mixture in develop branch. So there will be a pull request soon. And all the work should be available at the end of 2021 in an open repository for other users to use as well. And the next goal is to integrate this mixture models into the adjoint solver for optimization as well. So that was my talk. Are there any questions?
Okay, thank you, Mark. I really appreciate, in particular, your slides with comparisons against Fluent and numbers, and that's very much appreciated here. So there are a couple questions in the chat, so I'll read them out loud to you and you can take them. So the first one is there any limit to the number of species that can be simulated?
Okay, very good question. There shouldn't be any limit. Currently, it only works for a mixture of two. But I can change that very quickly, that it works for an unlimited amount of species. These mixing laws, it doesn't matter how many species you have. So that should work definitely in the future.
Okay, sounds good. And then there's another question. This one's from Pedro. He asked if Fluent, so the results you showed the comparisons for, if Fluent was run on the same mesh, and whether or not it was axisymmetric, or if you could explain a little more about the head-to-head comparisons.
Yeah, sure. So the exact same mesh has been used for Fluent and SU2, and also both cases have been run planar, so 2D, to have a valid comparison. Well, eventually it should work for axisymmetric as well, because I want to simulate the 3D flow instead of a 2D slice.
Perfect. Okay, actually we have a few more questions, so we can go a little bit long because we have the break next. So maybe we'll take one or two more questions here, and then we'll come back. We can bleed a couple minutes into the break. So another question is, what is the limiting factor of SU2 for better computational performance with respect to Fluent? I guess for your results here.
Yeah, so the residual of the scalar is still a bit that stays very high. So I should look into the convergence of the scalar solver, and that's probably the main thing I would say.
Yeah, I think something related might be the type of solver you were using. So there's actually another question about that. I assume that in Fluent, were you using a pressure-based solver or density-based, or?
Yeah, that's pressure-based. So
yeah, that could explain some of the difference.
Yeah.
Okay, let's see. We've got a few more comments here. So actually some appreciation. So some folks saying very nice talk. It's very much appreciated. Someone asks, how is the performance comparison done? What is the criteria to estimate that both have converged to the same level, for instance?
Yeah, so I've looked just at regular residuals, but also at some monitor points, for example, for whether the mass fraction doesn't change anymore at the outlet. For example, the mass flow average of the mass fraction of methane at the outlet. And I've also looked at that the imbalances are close to zero.
Yeah, sounds good. Okay, so with that, why don't we pause there? Thanks again, Mark, for a great talk.
I have a question.
Thanks for everybody for putting questions. Oh yeah, go ahead, please.
Unfortunately, I'm not very much into coding, but I follow from a distance, so to say. I'm very curious. I see in all the three, actually 4 presentations of today, the need of calculating properties. And I wonder if you all use the same class or each one of you has programmed a different model.
So I did not watch all the previous presentations, unfortunately, but I do think we use different classes. Each of us is working standalone on his own project, and
I see there's some work for us in the board.
Maybe I can
because
maybe I can jump in there.
Programs.
Daniel.
Sorry, Pierre, I didn't want to interrupt you, but I just wanted to mention that the fluid models that Mark implements are analytical models that are dependent on the mixture fraction and then are evaluated at runtime. And in the flamelet model, we use the table to look up these properties. So that's one difference.
Yeah, some ideas though. Okay.
May I ask also a small question? I mean, the comparison with Fluent was pretty good, but is there some experimental data to compare with?
there is some experimental data, but not for this comparison. There is only experimental data on the pressure drop and the CO2 emissions at the outlet for various heat output for the boiler. So that's I did not. This is only for one power output. So the simulation that you just saw was for 30 kilowatts, and in the future I can also run for also the other heat outputs, and I can make a similar pressure drop curve, and then I can compare with experiments as well.
Yeah, I mean, such comparison make the assurance in the result much better than when comparing just another software. Thank you.
Yes, true.